2.3 is systems of linear equations in two variables. A system of equations is a collection of one or more equations, each with one or more variables. And a system of equations can have exactly one solution, no solution, or infinitely many solutions. A solution of a system of equations in two variables is an ordered pair that satisfies both equations in the system. To solve a system of equations means to find all solutions of the system. So first, let's review solutions by substitution. With the substitution method, one equation is solved for a variable, and then that variable is replaced by the equivalent expression in another equation. Here's an example of a system that we're going to solve by substitution. So we solve one equation for a variable. Let's go ahead and take equation 1 and make it x equals y plus 3. Now if x equals y plus 3, then we know we can substitute that in for x into the other equation. So I have y plus 3 plus 7 equals 2y. Now I have a simpler equation in one variable that I can solve. That would give me 10 equals y. Now this solution is going to be an ordered pair, so I want to make sure that I'm solving for the x as well. So I'm going to substitute this back into either one of the original equations and solve for x. I'll go ahead and put it into the first one. So x minus 10 equals 3. That gives me an x of 13. So I have this x-y ordered pair solution of 13, 10. And we can check that quickly. 13 minus 10 is indeed 3. We can put 13 here and add 7, that's 20, which is 2 times 10, 20. That point satisfies both of the equations. We can also solve a system of two equations in two variables by elimination. Let's get right to example 2. What we want to do is make our coefficients of one of the variables to be opposites. I could easily do that by multiplying this equation through by 2. That would make it an 8x minus 4y equals 12. The first equation we don't need to change in this case. But now when I add these equations, I get 11x, the y's cancel out, equals 22, and I have a simpler equation in one variable. Again, our solution is going to be an ordered pair, so I need to take that 2 and substitute it back into one of the original equations. Let's say I put it into the second equation. 4 times 2 minus 2y equals 6. So in solving, I'm going to get a negative 2y equals negative 2, so y equals positive 1. My solution is 2, 1, and you can plug that into both of those equations and check to see that they are going to work, and they do. We can do a graphical solution. This will give you a little more insight into why we have to have an x and a y solution to these systems. We can solve this system graphically. So let's try, first off we need to get this into y equals form so that we can put it into our graphing calculator. I have a y equals 3/4 x minus 21/4. And putting this into y equals form, I'm going to have y equals a negative 2/5 x minus 9/5. Let's go ahead and use the graphing calculator now. I'm going to do 3/4 x minus 21/4. There you go. And negative 2/5 x minus 9/5. And let's do a standard window, standard zoom. And you can see those equations both being graphed on the same window. When you look at the blue line, every point, and there are infinitely many of them, every point that's along that line is a solution to that equation. Same with the red, every point that is on that line is a solution to the equation. So when we're solving a system of linear equations, we're trying to find the one point right there that is the solution to both systems at the same time. Once you have those graphed in your calculator, we're going to go into the Calculate menu. So Second, Calculate. We're going to calculate the intersection, first curve, second curve, and go ahead and hit enter one more time. You'll get the solution of 3, negative 3. Example 4 on break even. A company is said to break even from the production and sale of a product when the total revenue equals the total cost. That is, when R of x equals C of x, or if the profit equals 0. Suppose a company has its total revenue for a product given by R of x equals 5,585x, and its total cost is given by C of x equals 61,740 plus 440x, where x is the number of thousands of tons of the product that is produced and sold per year. Find the number of millions of tons of the product that gives break even and how much the revenue and cost are at that level of production. So to find our answer here, we have our R of x function set equal to the C of x function. That is where our revenue equals the cost, and we would break even. Okay. So if we go ahead and solve this algebraically, you can solve this any method that you like. Then we get 5,145x equals 61,740. And I divide 61,740 by the 5145, and I'm going to get 12. X equals 12. So what is that telling you? Well, X is the number of thousands of tons of the product that is produced and sold per year. So that's going to be 12 tons of product produced and sold will be our break even. We have no loss and no profit on that. The other thing that they want to know from this is the revenue and the costs at that level of production. if you look at your revenue function, the revenue when producing X number of tons So what does that answer mean for us? Well, X is the number of thousands of tons of the product produced and sold per year, and that's the number that gives us a profit of 0. So this will be 12 million tons of product will be our break even. That means we will not lose money, but we also will not make a profit if we produce 12 million tons of product. The next thing that we want to do is to find the revenue and the cost at this level of production. So your revenue function is 5585x. That means the revenue given this many millions of tons of product will give us this amount of revenue. So we just put the input of 12, our break-even number, and see what we get there. 5585 times 12, and we get the revenue when 12 million tons of product is produced and sold is going to be 67,020. So when 12 million tons of product is produced and sold, the revenue is $67,020. Okay, now the cost of producing 12 million tons of product is going to be 61,740 plus 440 times 12. We do 61,740 plus 440 times 12 in the calculator, and what do you know? We get the same. That's going to equal 67,020. So $67,020 is the cost when 12 million tons of product is produced and sold. So we found the place where the revenue is the same as the cost. That's when 12 million tons of product is produced. So when you take the revenue and you subtract the cost, you have 0. You have break even. No loss, but no gain. Market equilibrium. Quantity of a product that is demanded by consumers is called the demand for the product, and the quantity that is supplied is called the supply. In a free economy, both demand and supply are related to the price, and the price where the number of units demanded is equal to the quantity supplied is called the equilibrium price. If a price results in more units being supplied than are demanded, we say that there is a surplus. And if the price results and fewer being supplied than demanded, we say that there is a shortfall. Market equilibrium occurs when the supply quantity equals the demand quantity and when the prices are also equal. In this example of market equilibrium, we are to suppose that the daily demand for a product is given by P equals 200 minus 2Q. Q is the number of units demanded and P is the price in dollars. And that the daily supply is given by P equals 60 plus 5Q, where Q is the number of units supplied and P is the price in dollars. So let's take a second out here to specifically write out what variables we're using and what they represent. Q is going to be in place of where we usually have an X. It's going to be our independent variable. And it's either the quantity that is demanded or the quantity that is supplied. So we'll just say that this is the number of units. And then P is the price in dollars. So let's put dollars there. That's the price in dollars. And so every point on these graphs is a QP coordinate where the first number is the number of units supplied or the number of units demanded, and the second number is the dollar price. Market equilibrium occurs when the supply quantity equals the demand quantity and when the prices are equal. That is, when Q and P both satisfy this system. P equals 200 minus 2Q and P equals 60 plus 5Q. If the price is $140, how many units are supplied and how many are demanded? We can do this by putting $140 in for P. So let's do that on the first equation, which is our demand equation. 140 equals 200 minus 2Q. So we get negative 60 equals negative 2Q. So Q is 30. So this is the number of units demanded. If we put that $140 in for P in the second equation, which is your supply, then we end up with a Q equaling 16, and that's your supply. So your supply is a much lower number than the number that is being demanded by consumers. So we have a shortfall for this product. If you want to know what price gives market equilibrium, that's when the supply equals the demand. So you can set those equal to each other. So when we solve this, we get 7Q equals 140. So Q is going to be 20. So our quantity is 20. They're asking what the price is. You simply take that and put it back into one of the original equations. So your P equals 200 minus 2Q. If I put it into the first equation, I get this. So that is 200 minus 40, that'd be 160. So if you had a price of $160, that would give you market equilibrium. We can try this into putting this into the calculator as well. It's kind of neat to see. We've got 200 minus 2x and 60 plus 5x. And I'm going to set my window not with negative. We wouldn't have any negative number of units produced. And the x maximum Well, we had a 20 here, we had a quantity of 30 and 16. Let's just go to 40. And then we'll do a zoom fit, usually a zoom 0. We do that, we definitely see the intersection there. And when I calculate the intersection, it gives me an intersection of 20, 160. So at a quantity of 20 units, price is $160, and that is the same point on the supply as it is on the demand. That's the point that would satisfy both. You can also put in another equation here. If you had that price of 140, you could make another equation of y equals 140. And when you graph that, you see down here, this is your supply and this is your demand. So the supply with the price is over here, and the demand with that price is over here. Your demand is going to be a bigger number than the supply, so you end up with that shortfall. You can find those intersections as well. You calculate the intersection between, let's say, the red and the black. There you go. At 16 units, price of $140. There we go. That's your supply. You could do it again. Calculate the intersection of the blue line and scroll to the black line. And there we go. 30, right? 30 units with a price of 140. That's on that demand. Okay, so you're getting a larger number on the demand than you are the supply. You're getting a demand of 30 units on the demand number, and you're getting a number of 16 over here on the supply quantity. And that's what happens when you have that 140. If you go to put in another equation, let's put in that price of $160 and graph it, you'll see that it hits right there where the supply meets the demand, and that's your equilibrium. In this example, the figure is showing the size of the manufacturing sector of China and that of the United States in this century. Suppose the graphs for China and the United States can be modeled by these functions. You notice they've made them linear functions. They did some kind of a linear regression and simplified what these graphs look like with just a line. X is the number of years after 2000, and Y is going to represent the size of the manufacturing sector in trillions of the worth of 2005 dollars, the year of 2005 dollars, whatever the dollar is worth in that year. So we are going to find the year during which China reached the US on its way to becoming the world's largest manufacturer. So what we can do is put this into the graphing calculator. You can do these by hand as well using any of the methods that we did. We're going to use the intersection of graphs methods with the graphing calculator and play around with some of the window settings. I'm going to be trying out all the different window settings and zoom settings so that you're familiar with with this. Okay, now on the x-axis, we're going from 0 to 14. So let's change our window from, make it 0 to 20 so that we fit at least all those years in. And we'll do a zoom fit. Nice, you can see the intersection there. So you calculate the intersection, enter, 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 and at about 13 years, we get 1.9576636. So find the year during which China reached the U.S. on its way to becoming the world's largest manufacturer. That would be about the year 2012. So around the year 2012, we are equal in our manufacturing in measured in 2005 year dollars and trillions. With this investments example and in the following medication example, we're talking about mixture problems. So we have in example 7, an investor who has $300,000 to invest. Part of it's at 12%, and the remainder is in a less risky investment at 7%. If her investment goal is to have an annual income of $27,000, how much should she put in each investment? So let's start with the question of what they're asking us to find. They're asking us how much should she put in each investment. Well, there are two investment accounts she's going to have. So we're going to let X equal the amount invested in the 12% account. And we'll let Y equal the amount invested in the 7% account. If you take the amount that she invested in the 12% and add that to the amount she invested in the 7%, that would be her full $300,000 that she was investing. So we can make an equation out of that. X plus Y equals 300,000. And our second equation, we're talking about interest. She wants to get a total income of $27,000. So how much money is she making off of the first account? We know that she's making 12%, but what's the dollar amount that she's going to make from that? It would be however much she invested in that 12% account times 12%. So your interest is your principal times the rate. How much interest does she make off of the second account? She's going to make Y amount of dollars times 0.07 in interest. Principal times the rate is going to be your interest. You add up the interest from the first account, add up the interest from the second account, and you're going to get $27,000. Okay, now we can go ahead and get to the business of solving this. It's up to you how you do it. You can do it algebraically, or you can do it with the graphing calculator. I'm going to do it here with the graphing calculator just to help you get a little bit more practice in how to work the different things on your calculator. So I'm going to solve this for Y. Y is 300,000 minus X. And here Y is 27,000 minus 0.12x, all divided by 0.07. So let's go to the Y equals button, put in our equations. 300,000 minus X In the second one, we have 27,000. Let's make sure that we're putting this either in, put the entire numerator in parentheses, or another thing that you can do if you have the right operating system is hit alpha y equals, and that will give you this hidden menu of fractions. It gives you a template. So you put 27,000 minus 0.12 x, and that's all being divided by 0.07. Okay, and let's set our window from 0 to, well, how should we max that out? The most we could invest at 12% would be the full 300,000, right? So we can go ahead and set this at 300,000. We know we wouldn't invest any more than that because we only have 300,000 to invest. But then we can do a zoom fit and we'll see the intersection of those. So second, calculate the intersection, enter, enter, enter. And I get this intersection point of 120,000 and 180,000. Okay, so we don't want to get just a point. We need to make sure that we answer the question. So the amount invested at 12% is 120,000. 120,000. And the amount invested at 7% is going to be 180,000. And so we have our nice answers to that, just pulled right out of the coordinate where the lines intersected. In example 8, this is a mixture problem as well, but when we're talking about different percents of active ingredient or percent alcohol types of problems, I like to do a bucket method. This is just a visual way for you to organize all the information in your problem to be able to solve it. We have a nurse who has 2 solutions. She's going to add these, mix these 2 solutions up, add them up, and it makes this one mix solution. The one solution is 12% concentration. The other is 8% concentration. How many cubic centimeters of each should she mix together in order to obtain 20 cc's of a 9% solution? So here's your 9%, which is the mix. Inside, we're going to put the amount. Well, we want 20 cc's of that 9% solution when we're finished. How much of the other 2 that we have would we have? Well, that's when we're going to let x equal the number of cc's of our 12% concentration and y is going to be the number of cc's of the 8% concentration. So the thing that we would put inside here, which is the volume, that's going to be our x. This is going to be our y. Once we have that set up, what we do is find our first equation by simply drawing through there. That means I have an equation of x plus y equals 20. If you add the amount of cc's of 12% concentration to the number of cc's of 8% concentration, then you get 20 cc's. The other equation comes from pulling down through those buckets, multiplying as you go. So we have x times 0.12, that's 0.12x plus 0.08y equals 20 times 0.09. That's going to be 1.8. Where do you get that? Go to your calculator, put 20 times 0.09, and there you go, 1.8. So this is my system of equations that I want to solve. You can put it into your graphing calculator and find the intersection. You could use substitution, you could use elimination, whatever method you prefer to use on these. Again, I'm going to use the graphing calculator to give you more practice on seeing how that works. Follow along with me on your calculator. All right, go to y equals and put those numbers in. 20 minus x, and here, let's clear that out, clear alpha y equals, to get your fraction menu if you want to do that, 1.8 minus 0.12x, and that's over 0.08. All right, well, we know that we're only going to have 20 cc's of this mix when we're finished. So the amount of x should be somewhere less than 20. So that helps you be able to set where your window is. Let's go from 0, because we wouldn't have a negative amount of the 12% solution. And let's go up to 20. We can't have any more than 20 because 20 is what we want to end up with in our mix. So we'll do a zoom fit, and we see that intersection there. Go ahead and calculate the intersection. And we have 5 and 15. So the x is the number of cc's of 12% concentration. So that's 5 cc's. And the 8% concentration is going to be 15 cc's. That will add up to your 20, and that's that. Practice those. If those don't feel easy for you, it's just a matter of practicing until you start seeing how to organize the information and put it together into equations. Dependent and inconsistent systems. There are times when you have a system of equations that end up being the same line. Those are equivalent equations, and then the values that satisfy one equation are also the solutions to the other equation. And it ends up being the solution to the system. You'll end up with infinitely many solutions. So that's called a dependent system. One line's solutions is dependent on what the other line's solutions are because they are the same equation. Now, if a system contains two equations whose graphs are parallel lines and they have no point in common, so it's not graphed at the same place, then the equation has no solution. Such a system is called inconsistent. In this example, we're going to use elimination method to solve and see examples of these dependent and inconsistent systems. In the first equation, if I could multiply that through by a -3, it would cause my x coefficients to be opposite. So I'll go ahead and do that. It would be a -6x plus 9y equals -12. I don't need to modify my second equation at all. When I add these equations, not only does it eliminate the x, it eliminates the y and the constant. So I end up with this equation of 0 equals 0. This is a dependent system. You're going to have infinitely many solutions because this is the same equation, the second equation was just a version of the first equation where everyone was multiplied by 3. So we get infinitely many solutions, and we're going to say that that is a dependent system. When you graph, go ahead and graph here my first equation, alpha y equals, get our fraction menu up there, we've got 4 minus 2x, and that's all being divided by -3. And the second equation, we've got alpha y equals, and we will say 12 minus 6x, and that's all being divided by a -9. And when I graph, you see the blue line graphs first, the red line graphs exactly right on it. Even when we look at the table values, we can see that we have the same values for all of the outputs for given inputs. Okay, so that's a dependent system, and there are infinitely many solutions. Now, the solutions are in the form of anything lying on that line. With our second system, we have 2x minus 3y equals 4 and 6x minus 9y equals 36. Let's say that we multiply this first equation through by, again, a -3. That's going to give me a -6x plus 9y equals -12. Then I have the second equation. I don't need to do anything to it because these variables are going to now go away. But not only does my x go away, my y goes away. So I get 0 on that side equals 24. That's not a true statement. 0 does not equal 24. So these are going to be equations that are parallel lines that never cross each other. There is no point that will satisfy both equations at the same time. So this is inconsistent. If we go and graph these, then we can see alpha y equals, get our fractions in there, 4 minus 2x over -3. And here, alpha y equals 36 minus 6x over -9. Okay, and graphing, we see they're parallel and they're never going to cross. You look at the table values, you see they'll never have matching values at the same input. Okay, our last example is going to show a dependent system and how it applies in the real world. We have members of an investment club. They've set a goal of earning 15% on the money they invest in stocks. They're considering buying 2 stocks for which the cost per share and the projected growth per share, which are both in dollars, are summarized below. We have both the cost per share and the growth per share for utility and technology. They have $180,000 to invest. How many shares of each stock should they buy to meet their goal? So when you look at the question they're asking, how many shares of each stock, that tells you how to define your variable. We're going to say let x equal the number of shares of utility stock. And y is going to be the number of shares of technology stock. Okay. We have $180,000 that we get to invest. So that means that however many shares of utility stock that we buy, it's going to be $30 per share. So $30 times however many shares that we buy of utility. And we add that to the $45 per however many shares we buy of the tech stock. If you add that up, that's going to add to our total of $180,000 that we have to invest. Now our goal was earning 15% on the money invested. So let's figure out what that is. We have 180,000 and we want 15% return on that investment. So we're going to multiply by 0.15. That's $27,000. So our growth or our interest that we make on this is going to be 4.5 times however many shares of the utility stock. And we're going to add that to 6.75 times however many shares of the tech stock is going to equal the total of $27,000 in growth. Now, we have a system of equations that we can solve. Let's go ahead and use whatever method you would like to use. I can go ahead and put in y equals, give you more practice in putting that in. If you don't have that fancy alpha y equals fraction menu, then you can still do this with parentheses. 180,000, and we're going to subtract the 30x and divide by the 45. Then we have the other 27,000 and subtracting 4.5 x and closed my parentheses a little too early. 4.5 x, close the parenthesis and divide that by 6.75. Okay, and we want to know how many shares of each stock. Well, let's figure out how to set our window. If we have $180,000 to invest, and we decided to invest it all in the utility stock, then how many shares could we buy? 6,000 shares. So let's set our window from 0 to 6,000. Okay, and then we'll go ahead and do a zoom fit, and oh my goodness, we see it's the exact same line. Well, of course, we're wanting 15% growth overall, so whatever you invest in whatever, you're going to make 15% growth. So we have infinitely many solutions. We could invest however much we want in the utility and the balance of it in technology, or vice versa, and make your 15% that way. But we need to not just say that it's a dependent system or that it has infinitely many solutions. We need to make something that's usable. So let's go ahead and say y equals 180,000 minus the 30x, and it's all over 45. Okay, so infinitely many solutions of the form y equals 180,000 minus 30x all over 45. All right, so if they buy if they buy 1,800 shares of the utility stock, then how many shares of technology stock should they buy to meet their goal? Well, we can put that into our equation that we made. They've got, let's see, we let x equal our utility stock. So we're going to say 180,000 minus 30 times the 1,800 shares that we buy. And that's that. We're going to divide it by the 45 that we had there. And we get 2,800 shares of the tech stock. Okay, so we can double check that. If we do the 2,800 and you're multiplying that by your technology stock growth, which is 6.75, and you get that. And if we take the 1,800 shares and multiply that by its growth, 4.5, you get that. And we add those amounts together, then you should get your $27,000, which is what we calculated as being the goal of 15% on their investment of $180,000. With example 11, we have a problem of supply and demand. The table here gives the quantity of graphing calculators demanded and the quantity supplied for selected prices. The first task is for us to find a linear equation that gives the price as a function of the quantity demanded. Then we find the linear equation that gives the price as a function of the quantity supplied. Then we'll use these equations to find the market equilibrium price. I think it is of great help if we can identify in these problems what the independent variable and dependent variables are. So for this one, we are supposed to find a linear equation that gives the price. So your price is going to be here as a function of the quantity demanded. Usually we have a function of x. So P is going to be the y and Q is going to be our x in this instance. Go ahead and go into your stat editor and enter the data that we have in the table. Just double check to make sure you haven't typed anything in incorrectly as you go. We have our data entered, and now what we want to do first is part A. We're going to find the linear equation that gives the price as a function of the quantity demanded. So we're going to be using these as our x's and these as our y's. So go back to stat, calculate a linear regression. Our x we are going to pull from list 2, so replace that with list 2, and our y is coming from list 1, so change that to list 1. Let's go ahead and store our regression equation, vars, y vars. We'll save it in y1 and then calculate. So the equation that gives us the price as a function of the quantity demanded is P equals negative 0.5 Q plus 155. Part B, we're going to do similar, except we're going to make a linear equation that gives the price as a function of the quantity supplied. So this time we're going to use this column as our x and the price as our y. So go back into the stat editor. We're going to calculate a linear regression. This time we'll take our x list from list 3. Our Y list will still be the list 1. And we're going to store our regression equation again as a function, but put it in Y2. P equals 0.25 Q plus 50. When we put this into the graphing window, we want to make sure that we go from the smallest x that we have to the largest x we have, and we can adjust from there if we need to. Let's do a zoom fit. We see the intersection there, so we can find the equilibrium price. That's part C. So second, calculate the intersection. First curve, second curve, enter. And we see at 140, that's for the quantity that is both supplied and demanded, Y, the price, equals 85. So the market equilibrium price is going to be $85. That does it for this homework. So go ahead and try on your homework. Let me know if you have any questions.